Hello, my name is Andreas and welcome to my channel. Today we're going to have a look at a product based on lenticular technology. Lenticular technology, as we know, has been around for quite a number of years. In fact, I know someone who has played around with this technology attempting to create a stereoscopic display back 30 years ago using the CGA resolution. Now things have advanced quite considerably since then. We're going to have a look at one of the latest products that utilizes this technology to see what it looks like today. This tablet here is made by ProMa and is called the King tablet. So you may actually not be watching this video on my own channel. That's because I've given permission for this video to be used by specific other channels. So if you're watching on another channel, I just want to make you aware of what ANAVision is about. For me, the vision is to make 3D stereoscopic viewing known again. My vision is that people would open their eyes. And by that I mean both of their eyes. And normally when we look at things, we generally look at them flat. And I want to make 3D viewing known again. So please, if you are interested, have a look at my channel. You can find it by either searching for ANAVision on YouTube or simply by going to the link that I've got on the screen right now. So let's just start the device and have a look. And you'll notice that it has good colors. It's got a LCD display, but it's one of the high-end LCD displays, an IPS display. So the colors come out quite nicely. It also has a high resolution. The resolution is what probably impressed me most. It is probably also the most important for a display like this because as soon as you put a lenticular sheet in front of it, the resolution will be reduced. So this comes with a resolution that gives it a high pixel density, which will allow it to, if we put a high-pitched lenticular film on top of it, to then also retain that high pixel density in order to be able to view things stereoscopically with a good resolution. And that's the case with this display. So let's just have a look at the figures for that for a moment. The lines per inch for this lenticular film that's on top of this screen is 140 LPI. Now just as a comparison, I've got this postcard here. And this postcard is a lenticular, traditional sort of lenticular postcard that I'm sure you would have seen before. It's some kangaroos that I just picked up in Norseman a few weeks ago. And this one has a lenticular film on it that has a pitch of 75 lines per inch. So it's about half of what you have here. And you do notice that the density, the pixel density of this is quite reasonable. So having a screen that has a pixel density that is greater than this, well, that's quite good. That's a bonus. Now, to be fair to the postcard, there is a difference in that a postcard is autostereoscopic. It has many views, whereas the ProMa screen is stereoscopic. It has two views. And this boils down to a common trade-off that we see between resolution and number of views. There's this worrisome rock in this picture that was overhanging our campsite, high above us. I have to say, I only realized this as I looked at this photo in 3D. Okay, let's get stuck into the technical. What we're going to be looking at is what is the ideal viewing position for this device. And that's quite important because the position is relatively constrained and you don't want to get either fully or partially your left eye and your right eye mixed up. And that only happens in a particular position. And I'll show you why that is as we're going to go through this. Now, I know that for some of you, you've been waiting to get to this point and you want to know the technical details. And for some, this is the point you want to leave. So for those who want to go, I'm just going to give you the summary of what the results are. So the best viewing position for this device is between 35 and 45 centimeters from your eyes. That's roughly 14 to 18 inches. And you also have to have it fairly square on. So you've only got 8 degrees of tolerance, and that's 4 degrees one way and 4 degrees the other. And if you're within that, then you will have crystal clear viewing conditions. If you're not, then you may still get stereoscopic viewing, but it will not be necessarily all that ideal. Okay, with that, let's actually establish what that viewing position is. And for that, we need to understand a little bit about what's happening between the screen and your eyes. We can visualize this using a close-up of a pixel grid. On top of this, we will place a lenticular sheet, which up close looks like a whole number of rows of long corrugated plastic strips. Each strip covers 2 rows of pixels. Since the pixel rows are interlaced, each row has underneath it both a left and a right eye row. The orientation of the lens then bends the light so that the rows shine into the respective intended eye. Interestingly, the left row ends up in the right eye and the right row ends up in the left eye. This is interesting not particularly for this display. It is actually normal lenticular behavior. Now let's zoom out to the tablet level. And what we're interested in is what angle at which the light refracts, so that we can establish by how much we can tilt the device before we end up with the wrong view, where the right eye shines into the left eye and vice versa. So let's do this with a little experiment. So what I have here is an image, and that image contains 2 numbers, one for each view. Now we know we have 2 views, so there's not any more numbers. And currently we're on view number 1. And we'll be going into view number 2. So we're currently at a transition. You can already see number 2 partially. And we'll move that around this protractor until we hit the next transition. And that will tell us the angle that you can rotate within one view. Okay, so let's just do that. I'm going to look at the protractor, and we're going to move this until that next transition happens. And there we go. You can now see that it's starting to get into the next number. Right, so we're at about 9 degrees here. So let's just continue that just to see when the next transition happens. And that will take it back to number 2. And you'll see that's happening about now, around about 16. So somewhere between 8 and 9 degrees that we're seeing that transition happening. So we've got about 8 degrees within a particular view. Okay, so we've established that the angle is around 8 or 9 degrees. So as long as your eye is within that slice of the angle, we should be able to see correctly. Not quite. So far, we've only considered 1 pixel. Let me put another couple of pixels into this diagram here at the extremities of the device, just to make a point. Here you see that we get a mix of left and right eye into each of the eyes, and this of course is not desirable. So what ProMa have done is to tilt the edges inward like this. Think parabolic type mirror. We know that these type of mirrors have a focal point, and by pointing more inwards as you move towards the edge of the display also forms a focal point. In order to establish good viewing distance, we need to figure out what this distance is, what this focal point distance is. For this, let's do another experiment. So similar to before, I've got an image on the screen and I'm distinguishing between the left eye and the right eye. And the way I'm doing that this time is by color. And you'll see why in a moment. It's basically because I want to see the entire surface of the screen in one color if I'm just looking at one view. And as you're looking at it from your distance from the camera at the moment, you would see red and blue present. So you're too far away as it is at the moment. Now I'm going to use another camera. I'm going to use this camera here, my mobile phone. And I'm going to blend that in so that you can see what it's seeing as well. And you can see that it is still too far away. You're still seeing some blue and some red, in fact, about half and half. Now, as I move closer, we're going to get closer to this focal point that we're searching. And you can see that we're seeing more and more red, right? Until we don't see anything on the edges anymore, and it's just red. Okay, so I'm just going to center that, and we are just seeing red now. So let's just measure that distance. Okay, so that distance that we're getting now is about 45 centimeters, which is about 18 inches, right? So let's move that closer until we lose that. Okay, so we're now starting to get some of the edge turning blue again, right? So let's just move that back to where we just had all red. Okay, so about there. And let's measure that distance. So that distance there is about 35 centimeters, so about 14 inches. So it's somewhere between that distance of 45 centimeters and 35 centimeters that it's possible to see the entire surface of this tablet with just one view. And that's exactly what we want. Now I'll show you what happens when we move this camera closer. If we move this even closer, you'll see that we start to lose that focus again. And in fact, if we get really close, you're going to see multiple lines starting to appear because it's completely out of focus. You're just getting straight on pixels, basically. Quite interesting, really. We've established then that the ideal viewing distance is between 35 and 45 centimeters, roughly. And as I said, that's between 14 and 18 inches from your eyes. Now, as seen during the experiment, when your eyes are closer, you see multiple views starting from the edges. And similarly, when you move further away. Basically, when you leave the focal point of this parabolic mirror, so to speak, you lose the full stereoscopic view, and the left and right eye pixels start to overlap. The sweet spot then is right here in this green area. In this area, we are within 9 degrees, and we are within the right viewing distance from the screen. And here you get very clear and crisp viewing. The reason I dwelt on this a little bit is because I wanted to give you a guide for good viewing. It's a shame to look at a device like this and then miss the sweet spot and think it's not working. Okay, we've arrived at our last topic, and that's the topic of crosstalk. Now I've got our 1 and 2 image up again, but this time we're going to use it a little bit differently. Before we were interested in the transitions from the number 1 to 2 and 2 to 1. Now we're interested more in the center of one of those views to see if there is still any leakage from one view into the other left. What we're interested about is leakage in this case. So what I'll do for that is I will take, again, my other camera, my mobile phone, and I will move it. We've already established the correct viewing distance, so I've got that measured out. We're going to do this at 40 centimeters, at about 15 inches, and we're going to move it to the center of one of these views. So I'm going to choose view number 2, and roughly we're at the center of that now. And what I'm noticing is that it's quite good. The leakage from view number 1 is hardly evident in view number 2. I do notice it a little bit. I hope that comes up in the camera view as well. It's more the white that's leaking in the black that's noticeable, not so much the black leaking into the white. And that's quite typical of other displays as well. And in fact, I've not seen displays that do not have this sort of leakage. The only time when I've seen no leakage at all is obviously when you're wearing your VR goggles, because there is literally no possibility of any leakage. For a display, this is not bad. There's very little leakage from one view into the other. There is another type of crosstalk that we need to consider. And I mention this because you've seen now that this is capable of very little crosstalk, but you may encounter situations where there's much more crosstalk present than what I've shown you here, and you wonder why. And that's because crosstalk is not just a hardware feature, it can also be introduced by software. That doesn't mean that the hardware has suddenly more crosstalk. The crosstalk occurs at the software level. And with a tablet like this, being an Android tablet, it's quite possible for you to have the screen of your PC extended to it using some third-party applications. And actually that's quite useful. You can extend applications like Stereo Photo Maker straight onto your tablet, and you can see it in 3D. That's quite nice if you want to edit in real time using Stereo Photo Maker and view it here on this device. If you want to use Stereo Photo Maker in this way, all you need to do is place Stereo Photo Maker into vertical interlaced mode, and away you go. The problem, however, is that this can introduce more ghosting. It is not the tablet's fault, nor Stereo Photo Maker's fault. The issue lies with the screen extension application. These applications, and I'm listing a few here on the screen while I'm talking, they use compression algorithms in order to speed up the screen refreshes. Whilst this is not a problem, when you use it normally, any bleeding of a pixel in one row into another, even if ever so small, affects ghosting. So let me show you this based on my picture we've used before, focusing on this rock that started to play on my mind a bit. And you can see what the image looks like if I've viewed it directly on the device. And next to it here, you can see what it looks like when viewing the image via a Space Desk app. That's one of the screen extension apps using Stereo Photo Maker interlacing. You can see clearly that the rock shines through a little bit here, whereas it's much better if viewed directly on the device, as you can see here. So my recommendation for Stereo Photo Maker then is that you use it as an editing tool, not so much to view your final results. So wrapping up then, in the past we've seen a number of small 3D displays. We've seen it in mobile phones, we've seen it in the 3DS, we've seen it in the Fujifilm W3 camera. We've seen it in several places, but the screens have always been small. There have been a few larger ones, but this is now one where we see a high-resolution screen that's somewhat larger that works. And I think, in my opinion, the reason that works is because of this focusing of the views that I was talking about earlier. Now, I can't say that it doesn't happen in other displays. It's something I've just noticed recently. So I haven't checked back whether it happens in other displays, but it's certainly a contributing factor to making this display work. With that, we come to the end of this video. I'd just like to thank you for watching this video, and God bless.